Okay, and then so yeah, by that point we'll be at Grover's and Shor's algorithm, so two pretty big algorithms, and hopefully like you'll understand it by then and be implementing it in Qiskit. So yeah, just to get started with a plan for today, we're gonna start by quickly reviewing last week's workshop. I'm gonna go pretty fast, but just stop me if you want anything like in more depth. And then we're gonna talk about the block sphere, which is a nice way to visualize these quantum states. And we'll talk about the general single qubit rotations that you can perform on the sphere. Then we'll talk about Qiskit really briefly and sort of like how Qiskit works and how it integrates with the full quantum stack. And then we'll talk about one of these, like superdense coding and quantum teleportation. And we'll do the other one if time permits. So yeah. Just to get started with a review. So last time we saw how classically you only have a 0, 1, and you can measure it repeatedly and you'll just keep on getting that 0, 1. But with quantum, we're going to describe our quantum state with this generalized state. And so we have our two states that we're kind of now denoting in this bracket notation. So they're like they have the straight line on the left and the slanted line on the right. And then they also have their two coefficients, alpha and beta. And so when you measure it, again, we have the coefficient squared. And because these are probabilities of getting these results, the squares of the coefficients have to sum to 1. And importantly, when you do this measurement and say you get a 0 from this, now your state has just become the 0 state. So it's no longer in its like superposition. Does it make sense, everybody? Does anybody want a bit more detail on this? Okay. So next, we also talked about how you can take these general quantum states written as this in this sort of abstract bracket notation, and you can also write this as a more concrete vector that you can actually operate on. So we saw how you can take this sort of two-level system because we have a 0 and a 1, and then we can write it in sort of a two-component column vector as is seen here. And so the top one is sort of the coefficient of the 0 state, and the bottom value is the coefficient of the 1 state. So basically, we can take an arbitrary quantum state in bracket notation, and then we can write it as a column vector. Does this make sense? Okay. So then we talked about how if you have multiple qubits, we need to somehow describe their sort of collective system. And so we talked about the tensor product, which we denote with this, but also since we're lazy, sometimes we just omit this tensor product symbol. And we talked about how you basically just perform multiplication, like distribute it out, and you'll get a result like this. And we also talked about how the order matters inside the ket. So basically the state 0, 1 is not the same as the state 1, 0. Okay? Does it make sense to everybody? And then finally, we talked about how just like with one qubit, you can represent it as a column vector. Here, you can represent this as a longer column vector. So it'll have 4 entries because now we have 2 qubits. So the top, again, corresponds to like 0, 0, and then sort of increases in like normal binary. So 0, 1, 1, 0, and 1, 1. Everyone good? Next, we talked about once you have multiple states, they might not necessarily exist sort of like separately in their sort of product state. And what I mean by product state is like when you have just what we saw before, and you can sort of each state is well described by its own sort of ket or vector. Alternatively, like now when it's not in this product state, it's called entangled. Uh, and we talked about how when you measure one qubit in this entangled state, you automatically know the other state of the other qubit. So you can read this if you maybe forgot what we talked about last time, but basically there's some correlation between the qubits. Is this good for everyone? This is a bit more, um, I guess, complicated, or so if you have any questions. Okay. So then we talked about how you actually manipulate these states. So we talked about our quantum gates, such as the X gate, which is sort of like a quantum knot. So what it does is it flips between 0 and 1. So like X acting on 0 gives you 1 and vice versa. This is how you represent it as a matrix. And then if you want to see sort of it acting on a circuit, you have these wires, as we talked about last time, and you read them from left to right, and you have the X acting on it. And then you can basically verify that like this is what it looks like in the circuit diagram, and this is what it looks like as a matrix. And just know that the matrix goes on the left of your state because that's how matrix multiplication works. So another highlight is we talked about how gates are linear. And so basically that means you can fully understand how a gate works on an arbitrary quantum state, which is like this alpha 0 plus beta 1, just by knowing how it works on the basis vectors 0 and 1. Okay. Next, we introduced some other gates. So we had Z, which doesn't do anything to 0, but it gives a phase to the 1. And as I talked about, this does not do like this, where we go to a state -1, but it changes the coefficient by a factor of -1. So for example, if we look at this general quantum state, we basically go from alpha 0 plus beta 1 to alpha 0 minus beta 1. Does this make sense? Okay. Next, we have the Hadamard. And so before, whereas we saw like it kind of took one state to like one definite state, the Hadamard can take us from like one state such as 0 to a superposition, where there is some non-zero probability of measuring both states. So for example, it takes the 0 state to the state where there's a 1/2 probability of measuring a 0, 1, and takes the 1 to another state that also has a half probability of measuring a 0, 1. But you'll notice that the sort of sign or the relative phase, as we call it, is different. So this is a matrix representation. And yeah, I guess these two identities at the top, like this line, is pretty useful to just remember because we'll be using the Hadamard a lot. Yeah.
But what is like a superposition?
Yeah. So basically, um, sort of a superposition is kind of like a non-classical state where a classical state, um, so you can repeatedly measure it, you always get the same result back. And in quantum, if you have like just the 0 with a coefficient of like 1, if you keep on measuring it, you're guaranteed to get a 0, right? And like nothing happens to the state. But if we have, for example, like this, using our rule for how like we do measurement, you take the coefficient and you square it, right? So this state, you have a half chance of measuring a 0 or a 1, right? And so it's kind of in some sort of mix of 0 and 1. And so we just call that a superposition. Does that make sense? Okay. Any other questions on this? Okay. Next, we talked about the control gates, where you have this sort of black circle marking like this. If this qubit has the value 1, we're going to apply this U operation, which sort of just represents a general quantum gate, to the other qubit. And so that's just written out here at the bottom. And what this does is it basically allows us to perform entanglement because you can imagine that we will need some sort of operation that spans qubits to sort of create some correlations between them. And this also enables sort of conditional logic, like if this, then do this. So that's why these are important. So now moving on to new content. So is the review good for everyone? Everyone ready? Okay. So we've basically seen how these quantum states can be expressed as abstract kets with like alpha 0 plus beta 1 or as column vectors, but that's not really visual. And so it's nice to have just a visual way of representing them. And so here we're going to talk about the Bloch sphere. So basically every quantum state that we're going to work with, you can describe as a single point on a surface of this unit sphere. So maybe like the North Pole or like the South Pole or just anywhere on this ball. And so to make this a bit more concrete, the 0 state is the North Pole, the 1 state is the South Pole, and then the sort of superpositions we've been talking about with like this state that I just mentioned for your question, this is going to be like on the x-axis. And then sort of as we go around, we have other states, and sort of the whole surface is our regime of accessible quantum states. Okay, so in general, since this is sort of like in spherical coordinates, we can describe a general quantum state with the two coordinates like theta and phi. So theta will describe like how far down we are. So like this navigating downward is sort of dictated by theta, and then navigating around is given by phi. So basically theta is like the latitude and then phi is like the longitude. And so as we increase theta, we're basically saying our state is going to look more like the one state. And then as we increase phi, we're going to be sort of adding some sort of relative phase to the two states. And what I mean by that is you can see when we're at the sort of tip of the x-axis right here, there's like a 0 plus 1. But then as we start moving around, counterclockwise to the y-axis, you have this imaginary phase in front of the one, and we can just keep going. So we just keep on acquiring phase in this direction. And if you're interested, you can learn more about the Bloch sphere and this representation of quantum states. But for our purposes, you can just know that like you can represent quantum states on the Bloch sphere, and general operations look like rotations on it. So as we see here, if we apply an x gate to an arbitrary state, it basically looks like a 180-degree rotation about the x-axis. So we know that x acting on 0 gives us 1. And you can visualize this because the 0 state's on the top, and we act by X, it basically rotates 180 degrees down, and we know that the bottom state is the 1. So this is just one way of visualizing it. And then, so for example, the Z looks like a rotation about Z, and then Y uh, is a rotation about the Y-axis. So I didn't choose the Y operator yet, but that's just another one that exists. Um, so for example, we talked about how Z doesn't really do anything to 0, 1 besides multiplying it by either like 1 or -1. And that's kind of reflected by the block sphere, where if we act by Z to either the north or south pole, nothing really happens to it, right? It kind of just stays in place. So I guess you can learn more about these quantum states and gates by like what they do in the block sphere. Does that make sense to everyone? Any questions about the block sphere? It's not too important that you like have a strong understanding of it. I just wanted to let you know that this exists and it can be a helpful tool.
What
Yeah.
is phase?
Yeah. Good question. So phase, I guess, refers to the general concept um, when you have like the sort of complex plane. You can describe any complex number with sort of a magnitude and a phase. Right? And magnitude is saying like how far away are you from the origin, and the phase is like how much have you rotated along it. And so you can think of a phase just as an angle, basically. And so that's why this phi, which is just an angle, basically like on this sort of plane, which looks like the complex plane, it's just saying like how far around you are. That makes sense? Okay. So as I said, general rotations exist on the box sphere, and they have these sort of more complicated expressions that you can work with. But and this is not really going to be important for us. I just wanted to let you know that they exist. Okay, so now we're gonna quickly switch gears and just talk a bit about Qiskit and what we're gonna have to be using for the workshop later on today. So I guess at a high level, what we're doing is that we have these sort of abstract circuits that we've been developing, where we like take the circuit model and we apply like X and whatnot. But there needs to be some way of actually like synthesizing this down to quantum hardware, and so that's what you can do with Qiskit, and you can sort of basically I'll define some words of like compile and transpile, where this basically means like take an abstract circuit and then like bring it down to what we can actually do on quantum hardware. And so that's one thing that we'll explore a bit more about in the workshop. But to show how we like implement these abstract circuits in Qiskit, I'm just going to go through some of the commands you're going to have to use in Python later on. So also don't worry if you don't know much Python. Pretty much the only things you guys are going to need to know is what I've listed out here. So, and this is also going to be pasted at the top of the workshop just as a reference. So the going through the commands now. First, you can have this command called quantum register, and this is just going to create a sort of quantum register with n qubits. And what I mean by register is basically just like the set of qubits. So it's like the horizontal lines that we've been talking about. So it might, for example, like create this if you do quantum register 4. And next, we also might need classical registers to sort of measure our quantum registers into. So that's what the next command is for. And then now if you're going to consider both them together, you might just put them together using the quantum circuit command. Okay. Any, does anybody have any questions with this sort of notation, Pythonic? Yeah. Yeah. That'll come up actually a little bit down when it says measure. So maybe if you still have your question, then I can. Okay. So then to apply gates to these quantum circuits. Uh, Basically, if we take QC to be the name of our quantum circuit, we can just do like a dot H or a dot X to apply these gates. So we can have QC dot H, which is the Hadamard or H, and then we basically just select which qubit for it to go on. And so if you're not familiar with CS, then this indexing, like this bracket 0 close bracket, is basically just saying like take the first one. So everything is 0 indexed in this. Uh, and then there's also, for example, like X, and then you can also imagine like Z. So I guess there's a question. Okay, yeah. So there's just a question about how many quantum registers or qubits may you have in a real quantum computer. It doesn't matter in Python. So on a real quantum computer, they might range from like 100 to a bit more than that, or maybe lower. But that's the rough scale. And then in Python, since it'll be simulating it classically, um, it gets really hard to simulate when you get like higher up, like past 10 or so qubits. Yeah, question?
For C naught, do we have to use CX or can we type C naught as well?
We can see that as well. Like, yeah.
Okay.
You can experiment. I don't know off the top of my head. Okay, so we have C naught, which has this syntax. I'm gonna go a bit faster through this since I think you guys can read this when you get to the workshop part. And then you can apply general rotations, which we won't need here. So now going back to your question earlier about measurement and what classical registers do, is that basically when we have our arbitrary quantum state in the beginning, and then we want to say measure it and we get a result, but we want to store that result somewhere. So we can store it into the classical register. And that's just what commands like this do, where we have qc.measure the quantum register into the classical register. And so then we can like maybe read out from the classical register, but and you can like plot the results for that, and that's what is displayed below. So you can also visualize these quantum circuits with this command. And then here, I guess, is a bit more involved. So I talked about compilation and transpilation, which is how you take this abstract quantum circuit and you sort of optimize it for what it can actually run. So this backend is basically like a fake quantum computer that Qiskit will be simulating for us. And so that's what backend means. It's like a backend quantum computer. And then this command just says like transpile our quantum circuit for this backend. And then we're going to have a sort of compiled quantum circuit. And then from there, you can run this compiled quantum circuit on the backend with this command, and you can access the result of that run with a dot result parentheses. And then from there, you can basically plot the counts like this. And so you'll see this in the workshop. You don't need to know all of this off the top of your head because it'll mostly be there for you, but there'll just be like a few lines for you to fill in as an exercise. So these are some other methods that exist. Okay. Any questions about this part, I guess? Okay. So now we're going to talk about our first quantum protocol, basically like a simple algorithm for doing something useful. And so this one is called superdense coding. Or I guess maybe I should ask, for the sake of time, would you guys be more interested in learning about superdense coding or quantum teleportation? Where
That's teleportation.
so
I don't think that
I guess superdense coding is a way for us to transmit two classical bits with one quantum bit, and then quantum teleportation is the opposite, where we can transmit the information of one quantum bit with two classical bits. So I think I'll try to keep this lecture part short, and I'll probably skip one of them so we have more time to work on the workshop bit. And if you guys want, I can do the other one too. But which one do you guys want to start with? Want to start with superdense? Sure. Okay. So this is basically just gonna be our first application of just like doing something useful with the quantum gates that we've been building up so far. So you can imagine that we want to send information from, say, like me to Arav using some sort of quantum circuit or like quantum protocols, like sending my qubit to him. And we're basically wondering how many classical bits can we send using a quantum state? So is it just like, can we send one bit with a quantum state, two, or like more? So you can imagine that maybe I'll ask you guys, but just like some hints are that we have our quantum state in general has these sort of like two parameters in front of it. And these parameters, as we know, can be like sort of like arbitrary values. Like they can be like 1/√3 and like √2/3 and stuff like this. But then also when you measure it, you only get out like one result. It's like this or this, right? So I guess just with this as context, do you guys have any guesses for how much classical information you guys can send with a quantum bit? Any guesses? Okay.
The question.
Yeah. So basically imagine if I'm sending a qubit to you and I want to somehow send classical information to you through that qubit, and you can do whatever you want to the qubit after I've given it to you. How many classical bits of information can I transmit to you with one qubit? Yeah. So I mean, I guess I did ruin this from earlier when I was describing them briefly, but yeah, the idea is that you can send two with one caveat, being that you need to somehow use entanglement in this procedure. So there's this theorem which says if you're just sending a qubit with nothing else, you only get one classical bit out of that. And that comes from what I said earlier with like when you measure the qubit, you just get one classical bit, right? So it kind of makes sense that this is the most amount of information that you can extract. Yeah.
is that theorem Does it have like a name? Or is
Yeah,
it
it's
just called
the
the unfortunate hero?
it's the Olivo bound, or I don't know how to pronounce the name, but
I for a second I actually thought it was just called the unfortunate hero.
I mean, a lot of these theorems in quantum are called like no-go theorems because they like sort of ban what you can do. So you'll have stuff like that. I mean, so this if you want to search it up. Yeah, although the like formalization and its expression is actually quite technical. Um, but yeah, basically if you don't do anything special, you only get n bits of classical information out from n qubits. So we can sort of get around this by using entanglement. And you can imagine that like if we already share some sort of resource, so I guess we're going to kind of see how entanglement is actually like a resource, just like a classical bit or a quantum bit is. It's sort of like it holds some information in it that we can sort of bring out. Okay, so the idea for the rough sketch of what we're going to do and show is that if we have one person, so like me, and I want to send 2 bits to someone such as Ian, and say we start with a quantum entangled state, like the state at the bottom that we've seen before, I can do some sort of operation to sort of encode my 2 bits of information into our shared state and a qubit that I have, and then we can, or yeah, into like the qubit I have from the shared state, and then I can send it to Ian, and he can get out 2 bits of classical information, even though I've only sent 1 qubit. Okay, so that's the rough idea, and then now we're going to show that you can do this. Does everybody get the setup? Okay, so again, we're going to start with this entangled bell pair that we've seen before, and does anyone remember how you can construct this? I think it was in the workshop last time. Yeah.
HC naught.
Yeah, exactly. So you can apply an H to the first qubit. H is the Hadamard, and it brings you from sort of this 0 state to this 0 + 1 state. And then we can apply the C naught from the first qubit onto the second qubit, which again, you remember says that like if the first qubit has a state 1, we're going to apply an X to the second qubit, or we're going to flip it. So just to work through the math really quick, if we start with this state, the 0, 0 state, which is sort of like we both have a qubit prepared in the 0 state, and then I apply an H. So then we're going to get this resulting state and we expand out the tensor product. And then I apply a C naught from like my qubit to the other qubit. And then we're going to have this state, which you can verify, right? Like in this case, we're going to, yeah.
Can you just repeat what C naught does again? Sorry.
Yeah, so no worries, of course. C naught is the controlled X. So the C basically means the controlled, and then naught is analogous with X. And then we talked about earlier how when you have something like this in a quantum circuit, we have this like filled in black circle, and then it's attached with a line to another operation. And this operation sort of denotes the X. It's saying that you're going to apply this operation to the other register if the sort of black dot register is a 1. And so to make that concrete, when I apply the C naught to this state, this psi2, it basically distributes. So I'm gonna have C naught acting on 0, 0 and C naught acting on 1, 0. And in the first case, so remember that control is the green bit and the target is the red bit. So we don't do anything because the control bit is 0. And then in the second case, the control bit's 1, so we flip the second one.
Yeah.
Okay. So this is how we construct the Bell state, as this is called. And I guess you may comment that like in this sense, we are kind of like creating something before the procedure, like before I send a qubit, um, which is true, and that's like the only reason that we can do this. But the thing is, like, you can do this a lot in advance. So, for example, if I wanted to communicate with Ian in like a year, I could still like prepare like 500 Bell states, send his half to him, and then I could do this procedure like in a long time just by sending my 1 qubit to him later to send over 2 classical bits. So there's some sort of like you need to prepare for this procedure by making this entanglement. Um, and you can also think of maybe like you're getting this entanglement from another source. Like maybe you're buying it from Amazon, right? You're buying your one half of your entangled quantum bit from Amazon, and they send one to you and one to Ian. So like there's like some sense. And then after that, to do the procedure, I just sent him my 1 bit. But yeah, you do need to do this setup in a sense. Okay, so just for some notation, we're going to call the first qubit, so the left qubit in each of these states, QA, and the second one QB. And then let's say I want to, so I can be Alice and then Ian can be Bob. I want to encode 2 bits into the state and then I'll send it over. So basically, these are the possibilities for what I could try to encode, like 0, 0, 0, 1, 1, 0, 1, 1. And then we're basically going to say that depending on what I want to encode, I'm going to apply this to my qubit. And so you remember that these are all like one qubit operations. So I is the identity. I don't do anything. X is the bit flip. Z is sort of the like, it does nothing to 0, but it multiplies the 1 by -1. And then XZ is says that we do Z first and then we do X because you read it from right to left. Uh, does this make sense? Okay. So then now just walking through what this does to our collective state is that if I don't do anything, obviously I still have the same state. So that's what this is. And then if I apply a Z to my portion, so basically we're starting with this, and then I apply a Z to the first qubit, it's not going to do anything to the first state. So just to work this one out in more depth, like this. And then it basically distributes in, because we talked about how these operators are linear, or these gates are linear. And then can anybody tell me what it does to each of these? And we're only applying Z to the first qubit, although I guess it doesn't matter here. Yeah.
If it's one, then it will switch the sign.
Mhm. So what does the first state become?
First one, since it's 0,
Mhm.
it won't switch the sign at all.
Yeah,
And second one, since it's 1, it'll switch it.
yeah, exactly. So that's how we get this state here. And then doing something similar, if we have an X and we apply it to our starting state, we're going to get this. Can everybody see this, or should I go through it in more detail? Yeah.
Um, so when you have like two like a 0 and a 1, or like 0 and 0 or 1 1 together, are
Mhm.
those two like entangled qubits?
Yeah, so they're not necessarily entangled. I guess this state is entangled, but in other cases, you might see a state, for example, like this. And it has a bunch of zeros and ones for 2 qubits, but this is not entangled.
Why are there two qubits?
Yeah, so
Wait,
it's
so why are there two like numbers and
yeah. So the two numbers is because there are 2 qubits. So it's basically saying like this is a state in which the first qubit has a state 0 and the second qubit has a state 0.
okay.
And then there are like 3 other cases that it could be in when you measure it. So I think we went into this in a bit more detail in last week's lecture. So it's in those slides. Okay. So yeah, basically as we apply X, we'll get this resulting state. And then if we apply the last case, XZ, we'll get this resulting state. And so I guess, does anybody want me to work through these in a bit more detail, or do you guys just want to like trust? Yeah, sure. Okay. So let's basically show why if you apply XZ, you're gonna get this resulting state. And so I'm just gonna use a subscript 1 to denote that I'm doing this on my first qubit. Yeah.
Wait, the one with the X. Oh, those would be switched.
What?
The red one should be swapped,
Yeah.
right? But
Yeah.
instead of the black.
Yeah.
Or you mean like this one?
Yeah.
Or I mean, it doesn't matter because it's like
Yeah, it
symmetric.
doesn't-
It hurts with my brain because
It was
the one.
Do operations only affect the first qubit inside the
Yeah.
pair?
Yeah, and that's because sort of we're omitting the subscript by being a bit lazy, but here I'm just including it back again to show that like I'm doing it on the first qubit.
Okay.
But you could do like Z1, X2, for example, which would act on both of them. Okay, and so again, we read from sort of right to left. So I'm going to apply Z1 first, and I'm also just going to bring out the root 2. And we already talked about what happens after you apply Z1. And then I'm going to apply X to these states. So can anyone tell me what you get when you apply X? Sure.
This bit will change. So if it's 0 or 1, it is 1.
Yeah. So you get this out, right? Does everybody get that? Yeah. And then so you can just verify like this is the state we claimed it was going to be. Okay. Okay, so now after this encoding is done, so going back to a high level, I wanted to encode 2 bits. And so depending on what I wanted to encode, I applied something to my qubit, and now I'm going to send my qubit to Ian, right? So now Ian is going to have this entire state at his disposal, and he's going to want to try to extract out the 2 qubits that, or the 2 classical bits that I encoded into them. So, and I guess just as a reminder, he doesn't really have access to seeing what these states are. He sort of just has like two like quantum states, right? You can imagine it's sort of just like a nondescript package that he has, and he wants to somehow like analyze it to figure out what I encoded into them. So he can't see this directly, but we'll see that there's a way he can extract the 2 bits from this quantum state with measurements and some operations from his side. Okay, so to describe what Ian's going to do to extract his information, he's going to first apply a C naught. So in one sense, he's almost like reversing what I did, and he's going to get back the information out. So what happens after this? I guess yeah, we can do a bit more practice. So again, we're going to control from the first qubit, and then we're going to apply the target is the second qubit for the C naught. So can anyone tell me like what happens for this first state after applying the C naught? Yeah.
Will it be 0, 0, 1, 0?
Yeah. I guess I don't need to write that. So here. Same for the next one.
It's basically the same, it'd be 0, 0, 1, 0, but then
Yeah. Okay. So I guess one thing that I should show is that from this case, you can actually sort of like factor out the second qubit because sort of in each case it's a 0. So just by sort of normal product and multiplication rules and sort of distributing it, you can factor out this 0. So, question?
Wait, is the ones highlighted in red are the same qubit, but just the different probability?
Yeah, like a different state that the collective 2 qubit system could be in. Does that make sense? Okay. I think there's also a question in chat. So the question is, do the probabilities of the states have to be 1/2, or like in other words, maximally entangled to get out the information? So for this procedure, we do need these exact states. But like, yeah, I mean, I guess that's the question. Okay. And then same thing for the second case, where we can also like factor out the second qubit, where it's in this sort of definite 0 state. And what this means is if we measure the second qubit, we're also going to get a 0, right? And it's reflected in this overall quantum state, where in both of the cases, it's the second qubit is in a 0. Okay. Does anybody want to tell me what the result of doing the C naught on this state is? Yeah, I heard 0, 1, 1, 1. So take this, and then we can factor out the second qubit again. So we have this. And then finally, this one's, yeah, I guess I'll just show it. So in this case, we flip the first version, like the first case, and we don't flip it in the second case. And again, we can factor out this 1, right? So what you'll see is that we started with this very entangled state where, if I get a 0 in, for example, this state, I know Ian has a 1 and vice versa. And then we've ended after applying the C naught again with them unentangled, right? So now the 2 qubits are kind of independent, where the first qubit is in this superposition and the second qubit is a definite 0 or a 1. Okay, so we're starting to extract back out the classical information. You can kind of see like, 1 bit of it is sort of stored in this register, this qubit. Okay, so yeah, this undoes the entanglement. And then next, we're going to apply H on the first qubit. And so what happens is, as you remember, or as I suggested that maybe you memorize, this gets transformed to a 0, and then this gets transformed to a 1. And again, this is 0, and this is a -1. So we see that after this procedure from inside, we're going to end up with these as what is in our qubits. Does it make sense? So maybe the only nuanced one is why the last one has a minus sign. So that's just because if you remember, like the one state or like this state with a Hadamard goes to the one state, but this actually has a minus sign, right? So we just pull that out. Okay. So now, basically summarizing the full procedure is that I originally wanted to get these 2 bits to Ian, and so I did some encoding, and then I sent my qubit over to him, and then now he's done some decoding on his part, and then now he has these final states. And you'll see that there's like some flipping, so maybe you can just like read out the message from right to left, and you'll have recovered the original message, right? Does everybody see this? Okay. And maybe one caveat is that these are technically still like in the qubits, right? Like we haven't really extracted them out yet. All we've done is we've applied a CNOT and a Hadamard, but they're still sort of in the qubit, but we can measure them out to classical registers, or we can get a sort of classical result. And the point is that when we do this measurement, these qubits are in definite states, right? Like for example, this, when you measure the first qubit, what are you guaranteed to get? Well, it's a 0, right? And the second qubit, you're also going to get a 0. And so an important point is that all these measurements are fully deterministic. So basically guaranteed to get back out what I encoded in the first place, right?
It's a type of 0, 1, and 1, 0. It's supposed to be switched. It's supposed to be
Okay,
completely correlated.
sure.
Yeah.
No worries. Okay. Any questions about this? Yeah.
It's like the intended message 0, 1, but like the final is 1.
Yeah, so that's
It's
what.
supposed to be. It's supposed to be the same.
Oh, it's supposed to be the same.
Yeah.
Okay. I think that's what I'm saying.
Okay, any other questions? Okay, well, I guess here is sort of the biggest circuit diagram that we've seen yet, and this basically represents the whole procedure. So in the start, we started with 2 unentangled states in the 0, and we basically prepared the Bell state, which, as you remember, is the Hadamard and the C naught. So that's sort of this red part. And afterwards, I wanted to code some information. So depending on what bits I had, I either applied an X or a Z. And so these basically represent classical registers traveling down and like controlling this quantum gate of either a Z or an X. And so this basically represents the encoding portion in blue. And then afterwards, I've sort of given this qubit to Ian, and then he's decoding it, right? So he applies his C naught and he applies the Hadamard, and then he reads back out the results and sort of recovers my message. Does everybody get superdense coding? So I think this is pretty much the, yeah, I guess there's one more comment, and then we'll move on to the workshop. So I guess the expectation of superdense coding, or like what you might like think happens after what I just presented, is that we can like feasibly do this procedure. And then the reality is that because quantum states are so delicate, you really can't do this yet. So I talked about at the GM how your quantum states tend to decohere or basically like lose all the information in a matter of like microseconds, maybe even nanoseconds if you're not lucky. So yeah, you can't really do this unless you're really fast, or maybe you're doing like super dense coding from like this point to like this point, right? So you're not really doing anything yet. But the reason why this is cool is because it kind of shows you what is possible quantumly, and it gives you a measure of like what entanglement is like, where entanglement is kind of like a resource you can use, and how quantum bits and classical bits can be like sort of interconverted. And I guess, of course, like you guys might be thinking like, this is kind of silly anyways, because it's really easy to transmit bits, and it's presumably much harder to transmit qubits. But again, this is sort of just showing like what is possible quantumly. Okay, and so with that, I guess we can have another short poll. So do you guys want me to go into more depth on quantum teleportation, or do you guys want to get started on the workshop portion? Coding? Okay. So yeah, we'll get started on that. I think if we end early, maybe we can go back to this, but yeah, so let's go to QBraid. If you guys have not been able to access it yet, we'll come around and help you. But if you access the course that we talked about last time, you'll see there's chapter 2. And so from there, I guess I'll do a very quick outline of what is in that. Ian, can I pull up on your iPad or?